Hello dear students, welcome to this second session of discussion on unit nuclear physics of BSc 6th semester physics paper 1 of RCUB. So in the previous session we have already discussed the what is nuclear physics, what is nucleus, what are its constituents, then some of the properties of that nucleus, and after that we have also studied what is radioactivity, that is spontaneous disintegration of unstable nuclei to reach its stability with the emission of certain kind of nuclear radiations. So that may be alpha radiation or beta radiation and gamma radiation. Then we have also discussed some of the properties of those nuclear radiations such as mass, charge, velocity, then penetration power and other things. So in this class we will start with our actual syllabus. So in this session we will try to understand what are the properties of alpha radiations, even though we have discussed in the previous class. In continuation with that, we will try to understand other properties of alpha radiations, then what is alpha decay and theory of that alpha decay. So we will study one by one. So what are the properties of these alpha radiations or alpha rays? So an alpha particle is the nucleus of a helium atom consisting of 2 protons and 2 neutrons. So because of the presence of 2 protons, the charge of this alpha particle is plus 2 units, that is plus 2 into charge of an electron, that is about 3.2 into 10 raised to minus 19 Coulomb. Its mass is 4.001506 unified atomic mass unit, and these alpha particles are moves with velocity equal to 0.1 times the velocity of light. Then these alpha particles are not very penetrating, means the penetration power of these alpha particles is very much less in comparison with the other nuclear radiations, but they have highest ionization power, means they can easily ionize the air molecules, means the alpha particles have highest ionization power. That's why instead of using a thin sheet of paper, the air molecules itself ionize the alpha particles. So that's why the penetration power is very much less and ionization power is very high. So penetration power is very much less than beta as well as gamma, but ionization power is highest, means it is greater than the beta and the gamma. So these are the some of the properties of these alpha rays. The other properties are, so these alpha particles produce fluorescence in the substance like zinc sulfide and barium platinocyanide, means when we place a radioactive source which emits alpha particles in front of that fluorescent screen, when these alpha particles or radiations incident on that fluorescent screen, it produces certain flashes of light, and this process is known as fluorescence. So these alpha particles can produce fluorescence when we place these alpha radiations emitting radioactive source in front of that fluorescent screen. Then when the radioactive source which emits the alpha particles place in the electric field as well as magnetic field, they show certain deflections, means as the alpha particles are positively charged particles, so they are always attracted towards the negative plate. That's why they show deflections when we place them in the electric and magnetic field. So this diagram illustrates that deflection property of all nuclear radiations. So alpha radiations also show deflections, The beta radiations also show deflections because these two are the charged particles, whereas the gamma radiations are the chargeless particles, so they do not show any kind of deflections when we place them in the electric or magnetic field. So these are the properties of alpha radiations, that is the charge is positive plus 2 e units, mass, velocity, penetration power, ionization power, and the production of this fluorescence and showing deflection in the electric and magnetic fields are the properties of these alpha radiations. Then we will try to understand what is alpha decay. So if we consider any radioactive nuclei with atomic number greater than 82, atomic number greater than 82 means after that lead, they will spontaneously disintegrate. So radioactive nuclei with atomic number greater than 82, they will spontaneously disintegrate. The process in which an alpha particle is spontaneously ejected from disintegrating nucleus is called alpha decay. So the process in which an alpha particle is spontaneously ejected from the disintegrating nucleus is called alpha decay. So the general representation of this alpha decay process is like this. So we have a parent nucleus, its chemical symbol is X, it is having mass number A and it is having atomic number Z. So X is the parent nucleus having mass number A and atomic number Z. So it undergoes alpha decay. So we have daughter nucleus Y. So in this daughter nucleus, the mass number is reduced by 4 units, that is A minus 4, and atomic number is reduced by 2 units, that is Z minus 2. So parent nucleus is converted into daughter nucleus with the emission of one alpha particle having mass number 4 and atomic number 2. This is the general representation of alpha decay process. So where X and Y are the parent nucleus and daughter nucleus respectively. For example, means we will consider some of the examples for this alpha decay process. So the first one is uranium-232 undergoes alpha decay to form the thorium. Uranium-233 undergoes alpha decay to form the thorium-229 nucleus. Similarly, gadolinium-149 undergoes alpha decay with the formation of samarium-145 as the daughter nucleus. The third example is thorium-232 undergoes alpha decay to form radium-228 as the daughter nucleus. Similarly, platinum-175 undergoes alpha decay with the formation of osmium-171 as the daughter nucleus, and neptunium-237 undergoes alpha decay with the formation of protactinium-233 as the daughter nucleus. Like this, we have a large number of heavy nuclei which undergoes alpha decay process with the formation of certain daughter nuclei. So this is the alpha decay process. Now we will try to understand the theory of alpha decay. So we all know the nucleus consists of protons and neutrons. So out of these two particles, protons are positively charged particles and neutrons are electrically neutral. So because of this, you might have a question like, as there are only positively charged particles, then there must be a Coulomb repulsive force because like charges always repels each other. So protons are positively charged, neutrons are neutral, means there must be certain Coulomb repulsive force. Of course, there is a Coulomb repulsive force, but there is one more force which can easily overcome this Coulomb repulsive force, and that force is known as strong nuclear force. So that strong nuclear force is nothing but interaction between proton-proton, interaction between neutron-neutron, and the interaction between neutron and the protons. So this nuclear force is the charge independent force, so that all these 3 or 4 different interactions results in same amount of nuclear force, and this nuclear force is strong enough to overcome that Coulomb repulsive force. That's why the positively charged particles and neutral particles such as neutrons are present inside that nucleus. So along with this strong nuclear force, there is a Coulomb repulsive force. Because of that Coulomb repulsive force or the Coulomb field of the nucleus, there must be a potential barrier. So all the nuclei in radioactive substance do not disintegrate immediately to give alpha particles. There must be certain potential barrier or obstacle. So these alpha particles has to come out from that nucleus or come out from that potential barrier for the emission of the alpha particles. And the reason for this is the alpha particles do not have sufficient kinetic energy to overcome that potential barrier. That's why all the radioactive substance do not disintegrate immediately to give the alpha particles. For example, consider that the alpha particle pre-exists inside the nucleus before its emission. Means before its emission only the alpha particle is already existing inside the nucleus. If the alpha particle is considered to be separated from the nucleus of charge Z-2 into E. So Z-2 because the atomic number is reduced by 2 units with the emission of 1 alpha particle. So if the alpha particle is considered to be separated from the nucleus of charge Z-2 E by a distance r. So the distance between that alpha particle and the nucleus is r. Then the potential energy or the height of the potential barrier for the alpha particle to come out from that nucleus is given by with the help of Coulomb's law. That Coulomb law is given by V of R, that is potential energy or the height of the potential barrier is equal to 2 into E into Z minus 2 into E divided by 4 pi epsilon naught R. Then as we have E into E, that gives E square. So V of R is equal to 2 into Z minus 2 into E square divided by 4 pi epsilon naught R. So E is the charge of electron and R is the distance between that alpha particle and the nucleus, and epsilon naught is the constant, we all know. For example, if we consider uranium-238 as the parent nucleus which undergoes alpha decay. So for that uranium-238, the atomic number is Z is equal to 92. So by substituting all these quantities, if we calculate the height of the potential barrier for an alpha particle, so by substituting all these quantities, we can calculate the height of the potential barrier. So that is 2 into Z minus 2 means 92 minus 2 will be 90, then charge of the electron, and by substituting all those quantities we get that is about energy is equal to 26 mega electron volt. So this potential is attractive when the distance between that alpha particle and the nucleus is less than the radius of the particle as well as radius of the nuclei. So it is an attractive potential when small r is less than the capital R and particle is within the potential well. So that alpha particle is within the potential well, where R is the sum of radii of the nucleus and the particles. So if the interaction inside the nucleus is represented by a constant attractive force U exerted over a distance r, then this height of the potential barrier or potential energy V of r is equal to minus of U, where U is the attractive force, that is strong nuclear force, that is interaction because of that protons and neutrons. So from the above equations, it is clear that minimum amount of energy required is about 26 mega electron volt. So according to classical mechanics, from the above equations, 26 mega electron volt is the minimum energy that the alpha particles must have to overcome the potential barrier and escape from the nucleus uranium-238. So minimum energy is about 26 mega electron volt, which is in accordance with the classical mechanics. But in practical, it is not the case, because the radioactive uranium-238 emits the alpha particles of energies much less than the potential barrier. So that is energy about just 4 mega electron volt, which is very much less in comparison with that 26 mega electron volt. Therefore, this alpha decay process cannot be explained by classical theory, means the classical mechanics fails to explain this alpha decay process. So if the classical theory fails, then the scientist George Gamow from the Ukraine in the year 1928 explained this alpha decay process through the new principles of the quantum mechanics. The right side photograph is the scientist George Gamow's, and in the left side we have the variation of that potential barrier as a function of U, that is attractive force. Then according to this quantum mechanical theory, that is new principles of quantum mechanical theory, instead of escaping from that potential barrier, there is a small probability for that alpha particle to pass through that potential barrier, and this process is known as tunneling, and this effect is known as quantum tunneling or tunneling effect. It was explained by the scientist George Gamow from the Ukraine in the year 1928. So by 1928, George Gamow from Ukraine had solved the theory of the alpha decay via tunneling process. So he predicted that the alpha particle is trapped in a potential well by the nucleus. So classically it is forbidden, means it is not allowed to escape, but according to the newly discovered principles of quantum mechanics, it has a tiny probability, means a small probability of tunneling through the barrier and appearing on the other side to escape the nucleus, and this process is known as tunneling effect, or this effect is known as the tunneling effect. So this scientist Gamow explained or given the theoretical expression for the escaping probability of that alpha particle from the nucleus by this equation, that is log of lambda to the base 10 is equal to log of V divided by 2R to the base 10 plus 1.29 into ZD raised to 1 by 2 into R raised to 1 by 2 minus 1.72 into ZD into T raised to minus 1 by 2. So in this expression, the lambda is the decay constant and V is the velocity with which alpha particle moves inside the potential well, and ZD is the atomic number of the daughter nucleus, that is Z minus 2, because atomic number 2 has been transferred to that alpha particle, and T is the kinetic energy of the alpha particle. So by substituting all these, we can calculate that lambda, that is decay constant. By substituting all these quantities, we can also calculate the escape probability of alpha particles from the nucleus. So this is the theory of alpha decay. So in this class, means the summary of this class is, here we have discussed the properties of alpha rays, then alpha decay process and the theory of alpha decay. So in that theory of alpha decay, classical mechanics fails to explain this alpha decay process, whereas the quantum mechanics explains the theory of alpha decay, that is tunneling through the tunneling effect. So this is about today's class. So in the next class we will discuss about the range, specific range and ionization of these alpha radiations. Thank you.